Okay. Hi, everyone. My name is Julie. You can also call me Michael. I'm currently a research fellow at Gatsby Computational Neuroscience Unit at UCL.
And I'm Dimitri, entering my second year as a PhD student at Gatsby.
So we are the joint author of our new paper, which is called Optimal Rates for Regularized Conditional Mean Embedding Learning. So today, Dimitri and I are going to introduce some of the results from our new paper. So our collaborators also include Matthias Mollenhauer from Free University Berlin, and also Arthur Gretton, who is from UCL. So just a bit of background information. So our paper is going to appear in Europe's 2022 as an oral presentation. And so we are also going to attend the NeurIPS in person. So if you are interested in our work, so we can maybe also discuss at NeurIPS. I will first introduce our motivation. So our motivation starts with learning in the two random variable setting. So in the conventional learning setting, where we only concerned about random variables x and y, our objective to learn is the relationship between y and x, which is our target function here, fy given x. So this is nothing but the conditional mean of y given x evaluated at any point x. And to perform learning, we typically assume that our target function belongs to some h, where h is some reproducing kernel Hilbert space. And throughout writing this way, the target function evaluated at any point x is nothing but the inner product between beta and the phi x, where phi is the canonical feature map of our RKHS, and beta is some element of h. Throughout writing this way, we can formulate our empirical learning as the following optimization problem. So our empirical estimator f hat y given x is the minimizer of the loss function, which is the square distance between yi and the inner product between beta and the phi xi, plus some regularization term, which is the squared norm in our case. And since we assume beta to lie in the RKHS, which is potentially infinite dimensional, you might wonder that we might need to have an explicit form of our feature map phi so that we can evaluate this inner product. But it turns out this can be completely avoided once we introduce this kernel as feature dot product. So the inner product between any phi xi and phi x is nothing but the kernel evaluated at the point xi and x. And writing throughout this way, we can write out the solution at x as a weighted sum of y, where our estimator is the sum of beta I and x and yi, where the vector beta only involves the kernel evaluation. So our capital KXX is the kernel evaluated at any 2 points of our training data, and the small kx is a vector where each entry is the kernel evaluated at xi, which is our training data, and x, which is the prediction point. So looking at the right graph, we can see that the red lines are our feature maps, and the green line, which is our final estimator, is nothing but a weighted average of our feature maps, which is the red lines. Okay, so these are the conventional two random variable learning setting. However, in modern learning, we often encounter multiple random variables. So we not only have x and y, but also have z involved. So now our object changed to learn the f of z given x, which is the conditional mean of z given x evaluated at any point x. And we can write out this target function in the integral format, where this target function is the integral of the conditional mean of z given y with respect to the conditional distribution of y given x. And assuming again that the fz given y belongs to some RKHS, then we will have fzy evaluated at any y is nothing but the inner product between gamma and the phi y. And hence, we can write our target function evaluated at x as the integral of the inner product with respect to the conditional distribution of y given x. And this finally reduced to the inner product between gamma as well as mu y given x, where we call the mu y given x as the conditional mean embedding. And this is the conditional mean of phi y given x. So now we can see from the last equation. So suppose we know this mu y given x, then learning the target function of fz given x is the same as the two random variable learning setting as previous showed. Therefore, learning with multiple random variables reduces to learn the conditional mean embedding. So our core concept and core procedure is how we could perform learning of mu given yx. Okay, so as we discussed, our goal is to study the estimation of mu y given x. And this is actually an infinite dimensional regression learning problem, which can be tackled with infinite dimensional version of kernel ridge regression. However, there are a few types kind of gaps in the literature. Well, the first thing is that pre-existing works for optimal learning bounds require a finite dimensional feature map. This can be seen from Cabineto 2007 and Grunwalder 2012. And secondly, existing analysis of the misspecified setting usually make strong assumptions on the used kernels, as can be seen from Tawai 2022. So typically we'll assume a specific eigenvalue decay of the kernel, which is infeasible in practice. And therefore, in our paper, we are aiming to address these problems by making the following contributions. So first, we introduce the vector valued interpolation space to deal with the misspecified setting. And secondly, we provide matching upper and lower bounds for CMA learning without requiring finite dimensional feature maps. In other words, the dimensionality of phi does not matter at all in our paper.
Following this introduction from Michael, I will now introduce the formal learning setup and show you how you can learn the conditional mean embeddings through a vector-valued version of kernel ridge regression. We have a random variable x with probability distribution px and a random variable y living in curly y, where curly y is any space on which we can define a reproducing kernel Hilbert space denoted here as hy with kernel ky. Our goal is to estimate the conditional mean embedding seen as a function from x to hy. And this is in effect a regression task where the target phi y can potentially be infinite dimensional, but infinite dimensional or not, the natural population loss is an expected squared error loss, where here f is any squared integrable function taking values in hy. Starting from the population loss, the next natural step is to consider empirical risk minimization, but since L2 is too big for optimization, we consider a subset G of L2, and G will be our hypothesis class and is a set of functions from x to hy. And in addition, we will introduce a regularization term to avoid overfitting. Now, to design the hypothesis class G, we follow the classical construction from the literature on conditional mean embedding that is as follows. We introduce a second RKHS, this time on the covariate space with kernel kx. So we now have two RKHS, one for y and one for x. Then we look at a matrix E0 such that E0 times feature of x give us a conditional mean embedding. And since E0 maps feature of x to feature of y, a natural assumption is that E0 is a linear combination of outer product of features of y and features of x, which is equivalent to ask E0 to be a well-behaved large matrix in the sense that it admits a singular value decomposition, where the sequence of singular values is squared summable. That is always true in finite dimension, and in infinite dimension, those matrix or operators are called Hilbert-Schmidt operators. But this assumption is actually a smoothness assumption on the conditional distribution of y given x and the used kernels, in the sense that for any function h in hy, the conditional expectation of h of y given x should be a smooth function of x. And this is a sensible assumption, as we will learn the conditional mean embedding with limited data. So for values of x living outside our dataset, we want to interpolate, and this is easier if the variations are smooth. Finally, since we require smoothness, we call E0 a smooth operator. Next, plugging those modeling choices into our initial empirical risk minimization problem, we get the following. We optimize over matrices that maps features of X to features of Y with minimal empirical loss. And the regularization term is an Hilbert-Schmidt norm of the operator that reflects its smoothness. And this optimization problem has a good taste of admitting a closed form solution that has a very similar shape to scalar ridge regression. The estimator of the conditional mean embedding, mu hat, is the composition of E hat, the solution of our previous problem, with feature map of X. And this can be written as a weighted sum of the target phi yi with some coefficient beta I of X that are exactly the same as for scalar valued regression. The only thing that changes here is the target, which was previously a scalar and is now potentially an infinite dimensional vector. Now that we've seen an algorithm to estimate the conditional mean embedding, the next question, which is the main focus of our work, is what can we say about the performance of this estimator? And we have to distinguish two scenarios. The first one is when the target, the conditional mean embedding, lives in our hypothesis class G, which is called the well-specified setting. Second situation is when potentially the target lives outside our hypothesis class. That's called misspecified. Our contribution was to capture both situations with the help of what's called a vector-valued interpolation space, which is a continuous scale of Hilbert spaces that all lives between our hypothesis class and the L2, the space of squared integrable function. The parameters beta specify where in between each of the spaces is. So if beta goes to 1, G beta goes to G, or hypothesis class, but if beta gets close to 0, we get closer and closer to L2. So the main outcome of those ideas is to get a sentence like if our target lives in one of these interpolation space with parameter beta, then we should be able to control the rates with a factor that depends on beta. Think of beta as a parameter that controls the smoothness of the conditional mean embedding. If beta equals 1, the conditional mean embedding is smooth and lives in our hypothesis class, so we should be able to get a fast rate. But if beta gets strictly smaller than 1, the target is less smooth than one we'd planned for. We are still able to get a rate, but the rate will be slower than what we will get in the well-specified scenario. So to give you a rough idea of how we can build that kind of vector-valued interpolation spaces, we start by recalling that our hypothesis class was characterized by those big matrices from h of x to h of y, the space of Hilbert-Schmidt operators. And this can be seen as an outer product between h of y and h of x, a tensor product of Hilbert spaces. And from this view, we actually use scalar valued interpolation spaces. So interpolation spaces for h of x only that were introduced by Fisher and Steinwart. And this allows us to naturally define a vector valued interpolation space as a tensor product between h over y and a scalar valued interpolation space. And the situation is summarized in this figure, where if the parameter of the interpolation space is greater than 1, we are inside our hypothesis class. And if the parameter is between 0 and 1, beta here, G beta lives between our hypothesis class G and L2. We now have all the key elements to introduce the main result of our paper. We have a few assumptions. The first one is that Ky should be a bounded kernel. Second one is that the integral operator associated to Kx should have eigenvalues that decay at polynomial rate P. And finally, we have the assumption that the conditional mean embedding as a function of X lives in one of the previously defined interpolation space G beta. Under the three assumptions, we can control the performance of the vector-valued kernel ridge estimator. We get a rate that is both an upper and lower bound on the performance, and that is 1 over n to the beta divided by beta plus p. So for example, if we use a Gaussian kernel, p can be taken arbitrarily close to 0, and we get a rate of roughly 1 over n. But if we use a kernel with slower eigenvalue decay, for example, a Maton kernel, the rate is at least better than 1 over square root of n. The surprising result here is that the rates we get are actually independent of the dimension of hy. Those rates are actually exactly the same as one could get for scalar-valued regression with scalar-valued interpolation spaces. So that's the end of the content of this talk. You can find here the references we used. And finally, we wish to thank the Gatsby Charitable Foundation for their support. And you can find here our 2 papers, either on arXiv or on open review. And we wish to see some of you at NeurIPS for interesting discussions.